Yes. Well, also, it would be sad if I forgot to record this lecture 17.5, which is about divergence and curl. Divergence and curl. The two things my hair decides to do whenever I use my fuzzy shampoo. Let's see. Okay. As a matter of review, this is kind of going to put together everything onto one whiteboard from the entire first half of the chapter. So that's like, it's good to dial in here for a second. So put together everything that we've been doing. I'm going to use the whole board for each one of these. So there's two phases, okay? So the first version we've been talking about is all things about circulation and work. So circulation or work, however you want to think about that. And do you guys remember what the integrand is for circulation in this regular line integral? Yeah, f dot dr, which comes from f dot n or f dot t? Yeah, t. So f dot t ds gives you f dot dr. And you can also represent, so if you expand this dot product, it's basically f dx plus g dy. And I'm giving all the representations because this is going to be the comprehensive cheat sheet for all things that relate to circulation up to now, okay? So I like to organize, I developed this table last year when lecturing because it's kind of pretty. So we're gonna have one row here for f. What does it mean? What's in English? How do you interpret that?
The field equals the gradient.
Good, which means that f is what kind of a field?
Yeah.
Somebody said it over here, conservative. So if a field is ever presented to you as a gradient of something, automatically fill in f is conservative, okay? And so there's two options. F can either be conservative or it cannot be conservative. That's pretty straightforward. So f is either conservative or it's not conservative. Does that make sense? Now, there's two options for our curves as well. The curve can be closed and the curve can just simply not be closed. So we can have, let's look at what happens if the curve C is closed. So C is closed, and what happens? So if we have a conservative vector field, we're doing circulation over a closed thing. Do you guys remember what that was? Yeah, 0. So if you have a closed curve, then the amount of basically change in potential if you start and end in the same spot is just going to be 0 always. And then if you happen to not have a conservative field, you simply resort to using Green's theorem, which we talked about. And so Green's theorem then says, okay, well, maybe it's not just going to be 0, but I can still take the enclosed region from f dot dr and then do the double integral over R, which is the region that the closed curve is containing of the curl, where curl is gx minus fy dA. And that's Green's theorem. That's the first kind of way. Okay. And so if C can be closed, and guess what? C can just be not closed. So we can have an open curve, so C is not closed. And if C is not closed, then with the line integral, we can do with conservative fields the fundamental theorem of line integrals. So just in general, f dot dr is b of b minus b of a. Does this ring a bell for when we talked about the fundamental theorem? Okay. So that's conservative fields, you'll notice, are going to be always easier to deal with. Conservative fields are going to have 0 unclosed, and then also you can just do phi b minus phi a for not closed. So either way, it's actually pretty straightforward. It's a little bit more complicated if you don't have a conservative field, but we've talked about ways that we can still use these other theorems to make it work out. Now, say the worst case scenario and the most amount of work is if you don't have a conservative field and then you just got a random curve. See. So for that, the way you directly compute is just going to be using the integral. You convert your integral CF dot dr to be the integral from a to b, where a and b are t values, and then fx prime plus gy prime with respect to the variable t. Okay, so everyone get that into your notes. Then give me a thumbs up when you've got this. This is 4 sections in one little picture. And the longer you study it, the longer you see it, the more you're actually going to be able to use these integrations. You'll know the relationship between these different things. So all things conservative in general, when you're talking about circulation, conservative fields, you have the easier version. Not conservative, the more complicated version. So that's why we have things like grades here. And in general, closed curves, you'll notice, are a little bit easier to do than not closed. But yeah, so it's a good summary of all the definitions and formulas that we've got. Got it? Everyone good? Cool. Because now we're going to do the same exact kind of a table, but instead of being for circulation and work, what are we going to do it for? Flux. And that's the other side of this, okay? So what's going to happen is we're going to construct the table analogously. It's going to be pretty much identical in terms of concept and relationship. It's just we start using the different formulas that go in there. So we good if I write last call? Good?
Yeah.
Okay.
You're not here, are you?
Boyd's not here today.
What about Kennedy's out?
He's not here.
And that one?
Isabella's.
I know, he's- you know, someone's-
Flux. That's the other one. Okay. So if the circulation is f dot t ds, what is flux? And ds. And then the other representation that we see this in is the f dy minus g dx. So those are the two representations for Hohenlohe line integral. And so here, let's go through the list. Now we don't have things called conservative fields for flux. Okay, so the equivalent, the analog is going to be something called, there's going to be a stream function. And so in other words, if we can show that the field is the result of not a gradient, but this interesting cy minus cx. So if you have some function c, which is your stream function, if you take its partial derivative with respect to y, and that corresponds to the x component of the field, and then you have minus px corresponding to the y component of your field, or the g component of your field, then this is considered to be a special case. So analogous to how we can have a conservative vector field, this will be the analog for flux. This isn't as important, but it's what it is in the textbook. And so, and then the other way, you could basically either have it that way or it's just not. So that is not going to be one of these guys. And so again, it's simpler if it's closed. All right, so over closed before, what was in this box? We'll look back at your notes. What was in this box? What did the integrand go to?
0.
Yeah. So analogously, since this is acting as the same thing as conservative for circulation for the flux, the F dot NDN is going to go to 0 if they close. And in an analogous sense, what theorem was down here with this? Yeah, Green's theorem. So that's exactly what's going to be down here. Just the flux form of Green's theorem. So the closed C F dot NDS is double integral over the region R for the divergence, right? Because divergence for flux and curl with circulation. So this is divergence Fx plus Gy dA. And then if we're not closed, what was here? What theorem was here? And now in the previous set? Yeah, the fundamental theorem, right? And then so you can just evaluate. So this function C, again, it's analogous. And so it's going to be constructed as the F dot NDS is now being able to evaluate it at C B minus B A. Does that make sense? So do you see how it's like, it's different, but at the end of the day, it's not. I mean, so they're fulfilling the same relative roles as they are to the same definitions, just now altered for flux instead of circulation. And then the last one here, which is the least common by far, is going to be S dot NDS needing to be evaluated directly from the parameters to AB, then Fy prime minus G X prime ET. Okay, so there you go. That's 17.1 through 17.4. Wait, or 17.3. Yeah, no, 17.4. Yeah. Because today it's 17.5. Okay. Everybody give me a thumbs up for it. This will be really, really helpful. So in your notes, star the top of the page or something for when you are reviewing for this particular unit, because that right there is going to condense all of your notes and all of the main ideas into one page. For when that's always nice, having summaries. Does the layout of the table make sense for you guys? Is it something that you can use on your own, something that you would know how to read and get the information off of?
Yeah.
Okay. People finish marking off the last bits. Let me change the banner here. Let's switch over to divergence. You good, Marissa? Okay. Everyone else got this?
Sure.
All right. Going once. Going twice. Sold to the man wearing a Dorito chip shirt. My professor, Dr. Shelton, he likes getting snacks in class. And there's one time he asked people to tell us their favorite snacks. And someone just shouted out, "Flamin' hot Cheetos" from the back. And so he thinks that sounds like an oath. So now whenever I see a bag of chips that says "Flamin' hot Cheetos," I go, that sounds like an oath. Yeah, there you go. That's the question on the exam. Flamin' hot Cheetos categorized. Sounds like an oath. Okay, so let's actually define. So Rebecca asked a good question last lecture about where things come from in terms of the green form. So this is where we get to figure that out. So the divergence of a vector field, F that is differentiable on a region of Rn. So we'll give a general case first. is, and then the divergence of the field is equal to the del operator in a dot product with the field. Which is going to be, when you expand that out, f x1 plus all the way up to f. And if the divergence is 0, then what we say is that the field is source free. F is source free.
Is div short for differentiable?
Divergence of f. But you won't really see div f much. Most textbooks will just use the del dot f. Okay, as a matter of grounding this. Okay, so raise your hand if you thought this looked like a gradient at first. Okay,
Oh.
good, because that's what I want you to think of. This operator is going to act that way. And so don't forget that the way I want you to treat this now as a vector. It's not really a vector. But it can help. So we can apply this to different things. Notice that this is given generally. You will not have to deal with the abstract version. Okay, we're going to do R2 and R3. So R2, how many components should be in R2?
2.
Yeah, it's in the name. So treat it like a vector. So get the brackets. And so this is the same analogous to dx, except for now we're doing it for how many components we need. So the x component will be partial x. So it's like dx except for in partials of x. And what do you think the y component is going to be? Yeah, partial. Okay, and then in R3, so just as a reminder of what this del operator is, I should actually write that somewhere here. This is recall that this is the del operator. And then R3, well, del is going to look different, right? Because if it's an L3, we're going to have how many components? Okay, so what's the first one? Yeah. So to explain this, it's basically when you have a general arbitrary amount of components, instead of calling this x, y, z, since you don't know how many you have, you just call this x1, x2, x3, x4, x5, x7, blah, 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 to get that. So that's what this is, partial derivative with respect to x1. The first variable, the second, the third, the fourth, up to whatever, how many variables are different. So, but this is realistically what we're going to be doing. So I show you this, that textbook doesn't give you that, that's mine. This is what you'll actually be doing your calculus with. And if you so desire, do fun things and do everything in Rn. Okay, so the thing is, notice that the divergence is a dot product. Okay, and what we're going to talk about curl is going to be, what's the other product we can do with vectors? Yeah, that's going to be fun. Dot product for divergence, cross product for curl. It's built into the sound that will help you remember. So here, if we're then going to take these dot products of what the divergence is, we're going to actually start to see some similarities to what we've already done. Right, so in R2, the divergence del dot f, if I know that f is some f and g, then I'm literally taking this and taking a dot product with the f and g. So this is partial x, partial y in a dot product with f and g. Thumbs up if that's good, where those pieces are coming from. Because now you know how to do a dot product. These go together. The partial x with the f component, right? So f is being differentiated with respect to which variable? And then partial y with the g component. So g is being differentiated with respect to what? Two-dimensional divergence. You go and see your notes for Green's theorem when we did this. That is the integrand for the flux. Ooh. Yeah. So now with hindsight, you go back to Green's theorem and say, this is the double integral over divergence. to get plus, okay? And then in R3, it's going to be analogous. I don't have room on the board, but you can imagine if we have partial x, partial y, partial z, and then if I put it in dot with s and p and h, the only difference between the two-dimensional divergence and the three-dimensional divergence is just plus and then h set. Is that good? Okay. I trust that you know how to extend that application on your own. So let's do a quick computation just to make sure we got all the pieces in order. So, but here, I do want to make this very clear. If you make the del operator and write it out as like the partial x and partial y and all of that, don't try to do that in your head, please. Just write it out. It'll make a lot more sense when you're going through your work and doing the computation. So, for example, if I have the field f is equal to 4x minus 3, x plus y, and 2z minus 6. And I want to find the divergence. So what's the divergence of my field? Okay, well, divergence is which product? Dot or cross? Good, divergence, dot. It'll sound the same, start with a D, both of them. So del dot f, okay, this will give us divergence because it's the dot product. And so the del operation, now we're not explicitly told what to use for del, but give the context. How many components are with that?
3.
Okay, so how many components should del have?
3.
Which what are those going to be?
Partial x, partial y, partial,
And then, yeah.
partial.
Dot, and then we can just write down our field, right? So we have
4x,
4x minus 3,
x plus y,
x plus y,
minus 6.
2z minus 6. Okay, here's how you can write out your work. X components with x components. Or I should say first component with first component, because then there's multiple variables, it gets weird. But here we've got partial x of which one of those? 4x. Yeah, 4x minus 3. Plus partial y of what?
X plus y.
Y. So you guys tell me what comes after this.
Plus partial z times 2z minus 6.
There you go. Not rocket science. Although ironically, divergence is used in aeronautics. So there is that. It is kind of. So what is the partial derivative of this with respect to x? Oh. Okay, what about that one? And then yeah, it's plus 2. Okay, so with actual numbers, does that feel comfortable? The actual functions in the thing, how that actually plays out. Is that good? Thumbs up. You good, Jordan?
Oh, yeah, I'm good.
Okay, you good. What? Okay, we good?
Yeah.
Okay, let's move on with, well, do I want to tell you about the, I'll show it. There are certain things that I have to show you guys from the textbook that I personally think are boring, but you paid for the whole class, so you'll get the whole class. Okay, this is just a special case. It's a formula so that you don't have to do the derivation every single time. And things that prevent you from having to do the derivation every single time we call theorems. Let P be a constant. Then, given a field F is equal to R over the magnitude of R raised to the P power. Do you guys remember what this was called?
The
Radial, good, radial field. And the way I remember that one is whenever my hair goes straight out of my head. This poofs right out. X, Y, Z. I was thinking about like, there are a few things that mathematicians name correctly and some that they just don't name correctly. But curl they actually got kind of right. Because if you imagine I mean, the dudes maybe can't understand this one as much, but having curly hair, there's lots of rotation going on. And it's a measure of the amount of rotation. Whereas divergence would be more like just straight hair that's beaming out of your skull, but. Okay, so if this is true, if you have a radial field, then the way you compute the divergence has a really nice simplification you can do it. The divergence of a radial field is 3 minus p over the magnitude of r. Okay, so if Pearson gives you radial fields and makes you do this exercise, you have it in your notes. But in terms of being that exciting, it's not that exciting. Okay, let's move on to curl. Curl is where things get really, really fun because the del operation interacts with the cross product in a way that I think is just really visually pretty.
Yeah.
Yes. It's an epsilon in the mirror. And actually, just a little Greek lesson for you guys. When we say x in x, what we're really saying is that's coming from the Greek word n. And so this is an epsilon that's been stylized. N is a dative case, Greek preposition, which is going to establish that there's no motion, it is something contained within. Okay. Anyways, you don't think you'll need to know that until you're parenting your kids someday and they won't sit in their chair and you'll be like, you know what? Sit in your chair. Dative case, I want to see no motion, your butt in the seat, you are present in our minds. It's curl time. Curling, the most exciting sport ever invented. Okay. Definition. I want you to start thinking about the products. Okay. We started with divergence, which was which kind of a product? Dot. So as I'm writing this down, before I even get to the point, your brain's already like, oh, we're gonna get to cross. Okay, where's the other side? The other one. So all this stuff from chapter 13 really gets its comeback in the end here. So the curl of a vector f is equal to FGH. I'm gonna do this in 3 dimensions. I'm not gonna do it generally because the general cross product would be ugly here. That is differentiable on a region of R3. So notice we're now talking about 3-dimensional space. And then here's how it goes. So I'm gonna leave room to do this computation. The curl of the field is what kind of product? Of course. Yeah, good. Okay, so this is the end of the definition. I'm going to continue to extend it so we could show how you practically can compute this. So in R3, how many components should this have? Okay, so let's give them 3 components, which are what? Partial x, y. Okay, and then we need a field with 3 components, so let's just use the typical FPH. And again, treat this like a vector. Just ignore the fact that it looks like it's something else, okay? And if these were 2 vectors, like we learned at the very beginning of the class, you just put together the 3x3 determinant, I, J, K. And then on the second row is the first vector, so to speak. So we're going to put the components underneath. So we got partial x, partial y, partial z. And then on the bottom, we put these components of the second vector f, g, h. Ooh, yeah. So we can break this down. If we're gonna do the I first, so we cover this one, we can cover the top, I know you know how to do that, so just enjoy all the pieces coming together. As Kronk would say, oh yeah. It's all coming together. Okay, partial Y, partial Z, and then G, H. That's gonna go with I.
Mhm.
And then do we add or subtract the next step?
Subtract.
Good, subtract. And then it's the J stuff we're covering. So we're covering that middle one and we're covering the top again. So we got partial X.
Yeah.
And X is being related to what now?
H.
Yeah, so the partial Z, X and H. And that goes to K. Well, no. And J. This is like getting pulled over, right? Causing me like, officer, I have a meeting.
It's okay, Scott, we still love you.
It's just what I get. Okay. And then the very last piece is,
Partial Y.
well, so K stuff, right? So the
Partial.
partial X.
Yep.
Partial Y, F and G. With K. Okay, so big difference. Dot products give a scalar or a vector. Cross product gives what? Ah, okay, so divergence is more a measure, it's a magnitude, scalar value. The curl is actually a vector, and that should make sense, because curl indicates there's a direction. This is essentially telling you what direction this rotation is happening, okay? So a divergence is just emanating out, right? So it's just a quantity, whereas the curl is now, along with that, along with its magnitude, you need to know which way it's curling, essentially. And so that's why we present this in the form of a vector. It's going to have an X, Y, and Z component. And so we can actually compute these and just stick it in a vector. So the I component, if you remember the 2 by 2, it's cross minus this, right? So it's H with respect to Y, and then minus G with respect to Z. Wait. That is not the vector, that is just the component, so comma, there we go. Now, the only thing to be wary of is this minus sign. So normally we would do this one minus this one, but the minus sign flips it around. So we'll actually do F with respect to Z positive, is this minus a minus that, and then minus H with respect to X. Is everybody good with why this defies the normal order?
Yeah.
Because we subtracted it. So we flip the order because that minus sign is going to they're going to do a little do-si-do. What's the last component? What's the last component going to be? Yeah, GX
GX minus.
minus F. Boom. Okay, that is the curl of the field. So realistically, if you are good at here's what I would do. Because I have the memory of like a floppy disk from the 80s. Okay, so I would memorize that curl is a cross product. And that divergence is a dot product. And so when I get to computing a curl, I think curl, cross product, del cross F. Let me set up what that cross product looks like. And then I say, oh, okay. Because visually with practice, I can just be like, okay, so it'll be relating these two. If I cover up this one, I'll be relating these across. If I'm ignoring this, I'll be relating these. So can you brute force memorize this? Yes, you can brute force memorize this. Is that as useful as knowing this? No. So memorize this. This is just an exercise to remind us how to take that kind of a determinant. But this is what you really want to memorize. Because when you actually have components like an F, a G, and an H, you'll just stick it in and then actually do those partial derivatives as they come. Does that make sense?
Mm-hmm.
So minimize the work you have to do by just knowing this top line really, really well.
Two would just be like, same thing, except for it's one, it's a 2 by 2 vector.
Here, let me show you. So this will answer Rebecca's question with retrospect about Green's theorem yet again. Are we good if I rate this? Because this is kind of
almost.
Okay.
You like, all right, I'm good. Thank you.
Okay.
Well,
Is the two-dimensional case of this You good, Kobe?
Yeah.
Alright, lock it real good. Alright, so in two-dimensional case, when we're doing green theorem, we can confirm that that double integral is truly of curl, because, okay, let's practice. If I want curl, which product am I using?
Cross.
Good. And then this is going to be in the R2 sense, just partial x, partial y cross some f and g, right? Because we only have two components now. And so this determinant is a lot easier to deal with. It's just this 2x2 of partial x, partial y, f and g. Huh, interesting. G minus f y. Look familiar?
That's great.
So two-dimensional curl, three-dimensional curl. But this gives us the language to do the extension of green theorem curl into higher dimensions. In other words, double integrals instead of just, or triple integrals instead of double. Okie dokie, thumbs up would be good. Because now we'll get into more, let's say, the important one. Okay, as a means of review, divergence is which product? And the cross or and curl
Curl.
is
Related to cross.
okay. If you see a dot product, it's if you see a cross product, it's
Curl.
now if I want divergence, I take a.
Cross product.
If I want curl, I take a.
Cross product.
The reason I do that is because the dot product is
Divergent.
and the cross product is curl. Good. Okay. All right. Perfect timing. Immaculate timing. Atom clock level precision timing. 140 when I looked up. Okay. So we can really talk about this idea. Okay, so a big result that comes when I was alluding to the divergence and the curl being kind of these opposing ideas. They're not opposing in a sense, but they're kind of like opposite. One's has to do with being parallel, one has to do with orthogonal. So naturally they're gonna have kind of opposite properties and they cancel each other out. So show that the divergence of the curl in 3 dimensions, we'll just lock that down, is 0. Now, here before I finish writing this, here's the quiz. Divergence is what kind of a product? So, and curl is a cross product, but it's the divergence of the curl. So a curl spit or a cross product spit out scalars or vectors? So do you see how the curl, the vector, is the thing that we're taking the divergence of? So it's going to be a dot product where the vector that we're interested in happens to be a vector that's just the curl that we would find. And then on top of that, divergence will spit out what kind of an answer?
Scalar.
So is this 0 vector or 0 scalar? Good, all right. So that's saying that the amount of imminence, the amount of divergence that's happening, flows through a curve if you have curl is just going to be 0, and that makes intuitive sense. If you have a strictly rotational field, you're not having any measure of eminence, it should be 0. Okay?
So if you show that the curl of the divergence is being in the opposite around, you have it as a 0.
Let me think about this. You could do it in the opposite. Yes. We'll see how this goes. Okay. So here's the first line doesn't seem like it's that important, except for that it is. And so without this first step, this entire solution is wrong. Okay, so let's prove it. Prove.
Exactly.
Okay, so we need a field. Now here's how I can make this creative decision. I say, well, we're in R3, which means that I need to choose a field that is in R3, otherwise I'm doing irrelevant work. Okay, so F is just F, G, H. Okay.
What is PF?
Proof.
Okay. So something worthy of the special colored pen, right?
Sure, okay. That's what students say when, yeah.
Dr. Hoffman was pointing out the
You my Pearson. Yeah. as we saw, what's going to happen is we needed to take derivatives. We needed f, g, and h to be differentiable. If we don't specify that these are differentiable, technically we can do something completely wrong, okay, something that doesn't apply. So we need to make sure that f, g, and h have continuous second partial derivatives. Second partial derivative. Okay. We want our answer to actually exist. That is kind of why we have to say this. And then the divergence of the curl. And again, divergence is what kind of a value?
Scalar.
Curl is what kind of a thing?
Vector.
You gotta keep those two straight. You gotta treat curl as a vector. If you don't see curl as a vector and you try to turn it into some quantitative thing, you'll just throw yourself off. Okay. So a vector, this is the vector that we're taking the divergence of. This is okay, so divergence is which product, which okay. So we're gonna be taking a dot product of the divergence dot, but what vector is the vector that we're taking the divergence of? Yeah, the curl. So the curl in itself is expressed as what?
Del cross.
Say it louder, everybody. It's del cross f. So I use the parentheses to indicate that this is just a single vector. This is just one vector. This is the vector that we are then taking the divergence of. This right here is kind of the hardest part. Okay. The parentheses matter. The moment you take that away, you're like, what?
But you take the dot product of that resulting product.
Yes, this is a vector. This is the curl. And then we're taking the divergence of the curl.
Which is not gonna be.
So if I erased this and just wrote the English word curl in here as the vector, that's what I want you to think of. We're using these symbols to represent one vector, which is the curl. And then we're taking the divergence of that. Is that good? Okay. Yes.
This might not be a big issue, but we put like a vector symbol instead of a parentheses, right? We put a vector symbol, they would be wrong.
Yes, it would be. And here's the only, the motivation is correct. And then just the expression is the only thing that's not necessarily right. By nature of writing the del cross f, that is already implied to be a vector. So you don't need to, if I were to put that inside of vector brackets, then I'm making a statement that there's a vector whose component then is a vector. And then that's not necessarily true. So the parentheses are just indicating this is like a unit. Although I need multiple symbols to express one vector, that's okay. This is one vector and I'm taking the divergence of that. Is that good? Yeah, so use parentheses, don't put brackets around that. Okay, so then the computation's nothing crazy. I'd like you all, when you do this, show all of the work, please, and thank you. So del, we're taking the divergence of what? Let's elaborate on what this is. Well, this is b I j k of partial x, partial y, partial z, s, g, h. Okay, and then now that we've done the parentheses, now let's actually see what's going on in this dot product, right? So the del in R3 is going to be what?
Partial x. Okay, partial y.
It'll be sitting there and just like partial. And okay, so we already went through the derivation of this. But I'll just show you how I personally do this. If you think the way I personally do it does not help you, then don't do it. Do what works for you. But this is how, instead of memorizing the expansion, I can piece it back together like this. I just pretend like it's not there and I say, okay, so this little 2x2 is the focus. H at y minus gz. Hy minus gz. And then I think to myself, the middle one is the funny one. It gets flipped around because it's negative. So instead of going hx minus fz, that gets flipped around to fz minus hx. So fz minus hx. And then the last one, I pretend that doesn't exist. I'm just looking at this 2 by 2. And I go, okay, well then gx minus f1. Okay, so you can always check that. So this is starting to look like the example we did with just like the functions and numbers. And when we compute this, it's going to be exactly the same. So here, this is going to be equal to partial x of what?
Hy minus gz.
Good. Hy minus gz. What's next?
Partial y.
What's the relationship between the next two? What operator? Good, since it's a what kind of a product?
Dot.
Good, so you're adding all these up. So plus partial y, like Sam said. Someone else, what goes in here? Good, fz minus hx. Okay, what's the next term? Plus partial z of what?
F minus fy.
Good, dx. So far, so good. This is a good pausing point. Everyone good with why we needed to have a field with 3 dimensions?
Yeah.
Because it says R3. Is everyone good with why we need continuous second partial derivatives?
Yes.
Yes, we're about to take. Everyone good with divergence of the curl, not the English divergence of the curl translating to this. Okay, that's locked in because that's the most important part. If I can get solid thumbs up that you guys know how to get from divergence of the curl to here, that's all I need to know. Okay, is that good? Okay, and then setting up the del dot, then this expansion when you take out the curl, and then now you're just actually computing the dot product. And then now this is just a matter of like chapter 15 skill. It's nothing crazy. So hy, this is how I could use. So that because I'm dyslexic, so this is actually a legitimate thing I have to do to make sure I do it right. I write down the function h1, then I differentiate it with x, so I don't get everything twisted up. Okay, so write down the thing you're differentiating before you add on the next derivative. So minus gz, that's the thing, and I'm differentiating with respect to x. Okay, so in that case, what is going to be the next term? And then that one is minus hxy. Okay, here. What about this one?
G.
Gx and then with z.
Z
And then
minus
here,
fy.
fy with z. And then what I want you to do is really show me that you understand the mixed partials are the same, okay? So f, let's do the f's first. So fzy, where's the other f?
Minus
There it is,
fy.
minus fyz. And then the g's, so here's gxz, right? Gxz minus gzx. Z. Oops. GZ. I think G is my worst English letter of all time, actually.
Yeah.
Okay. And then the last, of course, the HYX minus HXY. And it's almost like we know by the Claral that this is 0 plus 0 plus the 0 equals 3. Okay.
So wait, in the,
If we're in binary.
equation.
You mean to tell me 0 times 3 is not 3?
Oh, that's what I'm saying.
Here's why it's not, because 0 is not the identity element with regular addition. No, 0 is identity for regular addition, 1 is identity for regular multiplication. And so the reason we can say for certain that 0 times 3 is not equal to 3 is the proof is simply that 0 is not the element that satisfies the identity property that returns back the element in the field of multiplication on reals. So you can actually prove the more pedantic things as you go higher in math.
And like, well, we're gonna get error.
Error.
All right. This is what we're doing. Contenda. Do you have any, can you do this? Do you have this in your notes? Josh, do you have this in your notes? Axel, you got this? Sam, you got this? Bella, you got it? Chloe, you good? Mark? Thumbs up, Danny? Got it? Michael? We good? Several questions, comments, concerns, good? Marissa, you good? Josh, feeling good? Rebecca?
What if for the fun of it slash the confusion of it, it turned into like F, Y, and then Y. Y, even though they were with the opposite sign in the previous step, would that be counted against us, or would it just be like, well,
If it isn't exactly like this, it's wrong.
Oh,
Now, there's some stylistic things that if you were grad students, this would just be trivial, so we wouldn't even be doing this exercise. But the point is, by having to interact with both the divergence and curl at this level of tediousness, that shows me you get this. So then it doesn't even matter what functions I give to you. If you actually can argue your way through all of that, then there's no field that I can give to you that you won't be able to not only do curls with and divergence, but then the relationship between curl and. So you see what the motivation is. It's not necessarily, it's obviously 0, right? That's the reason why this is a theorem, not just a computation. And so the exercise is, this is really putting together all of the parts of the calculus class that we've done. And saying, look, the culmination of all of our wasted efforts. And then you can show to your parents, I spent another $40,000 on education to be able to do this. Equal to 0. Cool. We good? You got this? Diego, you got it? Rem? Good? Jediah? Feeling it? Agonal? Good? Boy? Chelsea? Good? Alright. Alright, in that case, here's what I'm gonna have you do. Your exit ticket, I'm going to erase this. And then I want you to reproduce the entire thing on your own on a fresh sheet of paper. Show that to me, you're free to go, right?